All right, what I'm going to talk about now is just the first part of section 7.5. All right, 7.5 actually involves two ideas that are extremely related. One of the ideas is conditional probability, and then the other idea involves independent events. Okay, so what I'm going to talk about right now is conditional probability. All right, so let me motivate it in the following manner. Okay? Let us suppose that two fair coins are tossed. Can we find the sample space? I claim we can. Our sample space, well, we could have two heads. We could have a head and a tail. We could have a tail and a head. Or we could have two tails. All right, so having written out the sample space, what if I want us to find the probability of getting two heads? Well, again, the probability of an event is the number of elements in the event divided by the number of elements in the sample space. Well, all right, in how many ways can I get two heads? I claim just one. How many possible outcomes are there when we toss two fair coins? 4. So the probability is 1/4. Okay? So now let's suppose a little birdie whispered in your ear and you got some insider information. Okay? So suppose that you were told, hey, at least one of the coins is a head. Okay? So that was our little bit of extra information. And I claim with that extra information, that changes our sample space. Okay? So my new sample space is, well, if at least one of the coins is a head, we could have head, 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 tail, tail, head, but I claim that's where it stops. We can't have tail, tail. Okay? So now with this extra piece of information, what if we ask to find the probability that two heads appear? Well, again, that can only occur in one way, but now I only have 3 elements in my sample space. So with the conditional probability, essentially what's going on is that we're wanting to find a probability. However, we're given an extra piece of information. And with that extra piece of information, that changes our sample space. Okay? So, essentially, when we want to do this, let me write this out. So, given that some event B has occurred, we wish to find the probability of A. Now, your book uses a lot of notation for this. I tend to write everything out in English because in real life, things are given to you in English or whatever other language as opposed to just symbolically. Okay, so the way that's written is we want to find the probability of A, that slash means given B. Okay? Essentially, what's going to go on is the following. We reduce our sample space down to B, and then with that new sample space, then we find the probability of A. Okay, now your book gives a formula that in general I really almost never use because I like using my intuition as opposed to a formula. I am going to use it to motivate something later, but the formula that's given, and again I never expect you to memorize any formula, is the following. The probability of A, given that B has occurred, is the probability of A intersect B divided by the probability of B, again, assuming that the probability of B is not 0. Now let me just give you the idea behind this. First off, we have to assume the probability is not equal to 0 because it's illegal to divide by 0. Okay? So, given our idea of conditional probability, remember we reduce our sample space down to B, and then within the realm of B, we find the probability of A. Okay? So that's essentially where that comes from. Now, what I would like to do is present this conditional probability in a few different ways. One of the ways I'm going to do is I'm going to make a table, then I'm going to make a Venn diagram, and then I'll do an example using a tree diagram. Okay? So that's kind of our plan for the rest of this part of this section. So, let us first make a table. Okay? And really, yeah, I'm just going to make up the numbers off the top of my head here. So let's suppose we have the following, okay? A bunch of people are asked a question, and here's our table that we got the answer to. So like to ski, don't like to ski, and then we'll have total. And how about like to hike, don't like to hike, and then totals. This is not based upon anything other than what happens to be in my head right now. It's a sunny day. There's snow in the mountains, so skiing's on my mind, and then again, it's pretty nice out, so hiking's on my mind. All right, so I'm just going to randomly fill in numbers. So 40, 20, 60, 30, 10. Oh, how cool is that? It just happened to all add up to 100. Okay, so one of the important things here is knowing how to read a two-way table. All right? So let me just go through this. If I asked you the total number of people who like to ski, that would be 60 people. Okay? Of them, 40 also like to hike, and of them, 20 do not like to hike. The total number of people who don't like to hike, for example, is 30. All right? So if I asked you, what does this 30 represent? It represents the number of people who do not like to ski, but do like to hike. Okay? So what we're going to do right now is just find the probability. Oh, also notice that if you add across, that works, add down, that works, etc. All right, so what we're going to do now for all of these is find the probability a randomly selected person. All right, now we're going to go to town and find a whole bunch of probabilities. Before I do this, though, I want to say that I'm going to give you some keywords to focus on, and I'll write my hint to you over there, exactly how you should approach these. Okay, so let's first find the probability that a randomly selected person does not like to ski. Well, here's doesn't like to ski. How many people is that? 40 out of my total 100. And yes, we can simplify our fractions, or yes, you can put them in an equivalent decimal form. Okay? Just going to leave the numbers as they are so that you can see exactly where they came from. Okay, let's find the probability that a randomly selected person likes to hike. Well, how many people like to hike? 70 out of our total 100. Okay, now what if I want to find the probability that a randomly selected person likes to hike and likes to ski? Okay, so and is one of my key words here. And yes, when we do operations, and means multiply, and equivalently it means we're taking the intersection. Okay, we want both to happen at the same time. So how many people like to hike and like to ski? A total of 40 people. All right. Now I'm going to make a very similar question, but now I want to find the probability that a randomly selected person likes to hike or likes to ski. Or, yes, the operation is add, but the other thing that should go on in your mind is the union rule. Okay? For example, could you say, well, 60 people like to ski, 70 people like to hike, add them up to get 130 over 110? Or, excuse me, over 100? No, absolutely not. Number one, you can't have a probability greater than 1. That's nonsense. Okay? So let's ask ourselves, what's going on here? Well, these folks like to ski, and these folks like to hike. I claim we double counted. Didn't we double count these 40 people? So, be careful when you see the word or. So could you have said, well, listen, 60 people like to ski, 70 people like to hike, and then subtract off the amount we double counted? That's using that union rule that we've discussed. Okay? And yes, we could do it that way. Otherwise, you could say, well, what's 40 plus 30 plus 20? And we would say, oh, that's 90 out of 100. Okay? Moral of this story, be careful when you see the word or. All right. Now, let's do this probability. Boy, it's a bummer I write so big. Let's do this. We're still finding the probability that a randomly selected person, but now I'm going to say likes to ski if they like to hike. All right, so this is our first example of a conditional probability. I'm going to write that word down. Usually, you'll see the word if, or you'll see the phrase given that. Okay? That tells you that it's a conditional and we need to reduce our sample space. My best hint that I can give you is the following. You reduce your sample space down to the event that comes after either if or given that. Okay? That is my biggest hint. So, when you see the word if or the words given that, what should go in your mind is this is a conditional probability. It's a two-step problem. We're reducing our sample space. So let's first see what our denominator is going to be, because with conditional probabilities, our denominator tends to change. Okay? So in this case, we are going to reduce our sample space down to the total number of people who like to hike. So here's likes to hike. Those are the 70 people that we're talking about. Of those 70 people that like to hike, we're interested in the number that like to ski. Therefore, it's 40 over 70. All right, what if I want to find the probability that a randomly selected person does not like to hike if they do not like to ski? It's like a pretty contrary statement. All right, what do we reduce our sample space down to here? Whatever follows the word if. So in this case, we're going to reduce our sample space down to all the folks who do not like to ski. Here's the do not like to ski. So we're reducing our sample space down to 40. All right, so if we're only looking at this middle row here, what do we want to find? Well, these people like to hike. These people do not like to hike. In this case, we're looking at the people who do not like to hike, so it's going to be 10 over 40. Okay, so that's an example of a table. Now what I'm going to do is show you an example of a Venn diagram. And this will also give us practice in terms of filling in Venn diagrams, which is a super important thing. Okay, so let's suppose 200 people are in a room, and how about we have that 130 people, of those people, like to read. And how about 50 people like to read and knit? And 40 people in that room like neither. Okay? So, given this really interesting scenario, let's first fill in our Venn diagram. Okay, so these are my readers and these are my knitters. So let's fill this in. One number we can put in right from the get-go is the 50. 50 people like to do both. Another number we could put in is the 40, who don't like to do either one of them. Okay? Next, we have 130 people who like to read. We've already accounted for 50 of them. Therefore, I claim that 80 go there. Okay? Now, we still need to find this number here. Well, we've accounted for 130 plus another 40, so 170. So, given that there's 200 people in the room, and we've accounted for 170, that tells us 30 people go here. Okay? So, now that we have this set up, let's suppose a person is selected at random and and we want to find the probability that the person only likes to knit. Well, this is my knitting circle. It's kind of amusing. Anyway, this is my knitting circle. These 50 people also like to read, so we're really only interested in these 30 people who only like to knit. So we have 30 out of the total of 200. Now let's find the probability that the person likes exactly one of the two activities. In other words, we're interested in the people who only like to knit or only like to read. So only like to read is 80, only like to knit is 30. So here we'll have 110 out of 200. What if I want to find the probability that a randomly selected person does not like to knit? Well, again, we're out of 200. And if they don't like to knit, what we do is we cover up our knitting circle and we consider everybody else. We have those 80 and the 40, so it's 120 out of 200. All right. What if I want us to find the probability that a randomly selected person likes to knit if they do not like to read? All right. What's our magic word? It's if. If tells you conditional probability. So, what do we reduce our sample space down to here? All the folks that do not like to read. So let's cover up our reading circle. How many total people do not like to read? That's 70 people. Of those 70 people, that's all we can consider, I'm interested in the ones that do like to knit. Well, those would be the folks in that circle. So we have 30 over 70. All right, how about this? Let's find the probability that a randomly selected person does not like to read if they do not like to knit. All right, here's another conditional probability. What do we reduce our sample space down to? All the folks who do not like to knit. So, again, I'm going to cover up my knitting circle, and I have these 80 and 40. So now my sample consists of 120 people. Of those 120 people who do not like to knit, in this case, we're interested in those who do not like to read. Okay, well, these are the readers, so these are the ones who do not like to read. So we get 40 over 120. All right, we have one more type of example to go through, and this would be a tree diagram. All righty. So, tree diagrams are something that we're going to be using also in the next section, section 7.6. And so let's take a certain scenario going on here. Let me just draw you a tree in general. Okay, essentially you have some event A or not A. And then once event A happens, we have B or not B in both of these cases. Okay? Now, what's going to be going on here? I claim that the numbers that we put here very often in the problem will be given in percentage form. We write them in decimal form when we write our tree diagrams, okay? And what's going to go here is the probability of A. What's going to go here is the probability of A complement, okay? Now, let's look at this. We don't have the probability of B until A is established. So I claim implicit here, this is the probability of B given that A happened. There's a conditional. And this would be the probability of B complement given that A happened. And we could continue here. This is the probability of B given A complement. And this is the probability of B complement given A complement. Okay? These will be given to you. You'll see momentarily. All right? So, if those are given to us, sometimes we're interested in saying, hey, well, what's the probability of A and B? So, do you remember how I made that one comment about conditional probability in the formula? How I never use it in practice, however it's useful to show you something? This is the one place where it's useful to show you something. Okay? So, let's talk about the probability of B given that A happened. By definition, that's the probability of B intersect A divided by the probability of A. Now, you might recall when I wrote it the first time, I had A coming before B. But given the fact that I had A here and then B here, I had to go this way. Okay? Now, let's just say, I wish we could write that without a denominator. Well, how in mathematics do we get rid of our denominators? What we do is we can multiply both sides by our denominator. I can multiply on the left by probability of A and on the right by the probability of A. Okay? So on my left, I have the probability of A times the probability of B given that A happened. Don't worry about the notation. I just like to show you where things come from. Okay? On the right, these guys cancel, and aren't we left with the probability of the intersection? Yes. So I claim this gives us a beautiful way of computing things. Because suppose I'm interested in finding the probability of A and B. A and B means A intersect B. And what this formula tells us is take the probability of A and multiply it by the probability of B given A. In other words, to find the probability of any branch on your tree, multiply across. That's pretty cool. Now, the other way you can look at it is if you want to find the probability of A and B, and means multiply. Gosh, this is lovely. Okay, so let's actually take an example of a tree. So suppose a survey was given. And we have, say, doesn't really matter, 54% of the respondents were female. And then the rest were male. Of the females, how about, oh boy, doesn't really matter. 65% like green beans. Of the males, how about 7% like green beans? I'm not making any statement here. I wanted to pick a one-digit one somewhere, that's all. Okay, I claim we can draw a tree. Now notice with our tree here, one of our probabilities is just given straight up. And notice the second event and the probability associated depends upon the first thing happening. Okay? The point that I'm trying to make is when you're drawing a tree, you need to figure out what is your first branch and then what is your next branch. So I claim over here that my first branch is going to be whether or not people were male or female. My second branch is going to be about their taste of green beans, because notice the percentage depends upon whether these people were male or female. Okay? So if I'm to draw this tree here, let's do it. So, what do we have? We have females and males. Well, 54% of the respondents were female, that's 0.54. If the rest were male, that would be 0.46. Each of these guys, when you add them up, have to equal 1. Okay? And then we're going to talk about light green beans or not light green beans. Of the females, in other words, we're here, what do we have? 65% light green beans? Well, if 65% light green beans, then 35% do not. Of the males, 7% light green beans. Okay, the reason why I wanted a one-digit percent is it is not 0.7, it is 0.07. Okay, so 7% light green beans, then 93% do not. Okay, now I'm just going to ask us a few different questions. Let's find the probability a randomly selected person was male and did not like green beans. Notice we have the word and. Okay, that tells us intersection. Okay, will you grant me that we're interested in this branch? We want this person to be male and we want them to not like green beans. Okay, remember what I said, the way to find the probability of a branch is to multiply the probabilities along that branch. Oops. So 0.46 times 0.93, you're going to get 0.4278. What if now I want to find the probability that a randomly selected person, how about this, did not like green beans? Okay, well, we can look here and we can say, oh boy, wait a minute, these people don't like green beans. Neither do these people. Will you agree that of the folks who don't like green beans, they could be females and not like green beans, or they could be males and not like green beans? All right. See, in here I wanted to find the probability of both. I specified that I want this person to be a male and not liking green beans. Here I just want to find the probability that a randomly selected person does not like green beans. So female and not like green beans would be 0.54 times 0.35. What operation does OR tell us? Add. Male and not like green beans is 0.46 times 0.93. And if anyone really cares, I will compute this other one. We're going to get 0.6168. Wow, that's a high probability. All right, so one more question associated with this tree. Let's find the probability that a randomly selected person does not like green beans if they were male. All right, now I'm intentionally using the same types of things, and I want to show you the difference here, okay? There's a difference between part A and part C. In part A, I wanted to find the probability not only that the person was male, which is 0.46, but also that they do not like green beans, which is why we multiplied. I claim here we've got a key word, and our key word is if. Now what we want to do is find the probability that they do not like green beans if they are male. In other words, we reduce our sample space again down to whatever comes after the word if. In other words, we're reducing our sample space down to males. Okay? We're here. When you have a problem like this, inside you should be jumping for joy. Okay? Because we're assuming we're here. So, if they're male, now we want to find the probability that they don't like green beans. Just read it off your graph. It's 0.93. Well, let's just do a couple more here, just so that you guys are straight. How about this? Let's draw one more tree, and then we'll do a few more probabilities. Might as well get some more practice drawing a tree also. So, I'm going to keep the basic framework here. But now my story is going to be slightly different. Let's suppose, here, I'll write the story down here. Well, scenario, let's say. Okay, so suppose bicycle parts come off of two machines. 70% come off of machine A and 30% come off of machine B. Of the parts coming off of A, how about 3% are defective? And of the parts coming off of B, let's say that 12% are defective. I think they need to fix machine B. Okay? So I think you'll grant me that the first situation or the first branch of our tree is whether or not the parts come off of A or B. Because the probability of them being defective depends upon which machine they came off of. So first we have A and B, and this is 0.7 and this is 0.3. Notice they add up to 1. Now they could be defective or not defective. Defective, not defective. And of the parts coming off of A, 3% are defective. That's 0.03. Therefore, aren't 97% good? Yes. And the ones coming off of B, 12% are defective, and therefore 88% are not. All right. So now that we have our tree drawn, I kind of have to change the wording of the problem. Find the probability that a randomly selected, how about bike part? Okay, part A is not defective. All right, this is one of our situations where we could have more than one possibility. This is not defective and this is not defective. Do you agree they could come off of machine A and not be defective? Or they could come off of machine B and not be defective? All right, coming off of machine A and not defective, I claim is this branch right here. So 0.7 times 0.97. What does OR tell us? That tells us plus. B and not defective, that'll be 0.3 times 0.88. Okay? And I'll let you guys just multiply that. I think you can do that. All right. Now let's find the probability a randomly selected bike part came off of A and is defective. Okay, now I'm interested in the part coming off of A and being defective. That would give me my top branch, which is 0.7 times 0.03. That's a teeny tiny probability. Okay, 0.021. Okay? So, last but not least, let's find the probability a randomly selected bike part is not defective if it came from B. All right, what's the key word here? If. We're reducing our sample space down to the fact that we know this bike part came off of B. Okay? So, if it came off of B, we want to find the probability it's not defective. That is 0.88. All right, that concludes the first part of section 7.5 on conditional probability. Next time we will talk about independence. Thanks.